Hello! So exciting. We are now starting our engine project. And the very generous people at Kingwood High School have donated some parts for us. So what I have here is the connecting rod, wrist pin, and piston off of a Acura. Now, interesting thing, if you think of Acura, you might first think Japan. But upon measuring the dimensions of this thing, it lines up with, surprise, inches better than millimeters, which means it's actually made in North America. And I Googled it, and sure enough, Acura is now produced in Ohio. We're going to start out with a piston. It looks like a cylinder with some stuff carved out of it. There's actually a little bit more to this than meets the eye. We will talk about the oil control ring, the compression rings, how those valves are going to sit on the top of it, the skirt, and how it's going to rub against the walls. This is actually not a straight cylinder. All of the combustion happens at the top, which means the top is really hot and will expand versus the base is not quite as hot, does not expand enough. So you have to put in some material thermal properties in determining the dimensions of this thing. It's going to be using a tapered extrude for that point. And hopefully this will be kind of an interesting introduction to engines and how engines work. And I'm super excited to have some actual parts to take dimensions off of this year. Zooming in on this, we have a diameter of 3.5 inches or radius of 1.75. I'm actually going to just make a quarter of this and revolve it around the center. So we'll have a rectangle 1.75 and a height of 11/16. And you can actually put these things in as a fraction, those three significant figures showing up. The fourth significant figure, it's 11/16 high. Okay, 3 divided by 16th for this top lid, going back 1/8 of an inch or 0.125 inches. And then we're going to come down 1 divided by 16, back over 1/8, 0.125, down 2 divided by 16, over 1/8, down 1 divided by 16, over 1/8, down 3/32, or 1.5 over 16, over 1/8, and down another 3/32, or 1.5 over 16, over 1/8, and that should bring us 1 divided by 16 back to our base. So completing this top portion, turning these back into regular lines, finish sketch, and we're going to use the revolve command. Select our area, and the axis is this left side of the rectangle, 360 degrees revolution, and there you have the top. Just a few notes about the crown of this thing. So the combustion area happens right above the piston, and in here you can see the valve recesses. So we've got intake valve where the air and sometimes fuel is sucked in. Sometimes the fuel goes directly to the combustion chamber. And then there's another 2 valves where the exhaust is then pushed out after the combustion happens. Some interesting carbon buildup on this that indicates that there was a little bit of oil leaking out of those valves that then burnt on the top of this. And you can check your seals and some of the engine performance by looking at carbon buildup in here. Gasoline is actually a solvent. When you used to add gas to the valves themselves, the gas would clean the valves, but now you want to really cut back on the amount of gas you're using and get fuel efficiency. So the new injectors that go straight into the combustion chamber themselves, they don't clean the valves out as well, and you can get some carbon buildup on the intake side. The exhaust side, at this point, you have very high temperature gases, and just the high temperature will usually burn off and keep those valves clean all on their own. Rather than putting these guys in now, I'd like to kind of build the rest of the engine, see how those valves are going to set on the top of this thing before actually placing. The volume of the combustion chamber is actually really important. If you get a very small volume, you'll get a higher efficiency. So you have the top dead center, bottom dead center. Small area, small volume means high pressure, that you're compressing those gases into a very, very small area up here. The smaller the area, the higher the pressure you will get. Going on to the skirt of this. High temperature, not quite as high temperature. So because metal expands when it's hot, the top of this will expand more than the skirt will expand. So there's actually a little bit of a taper on this where the base is larger than the top, because the top, when it gets hot, will expand out a little bit. It is also not circular around this, and that is how the force is. So during the power stroke, so you light the fuel on fire, you have high pressure that's going to shove this thing down, turn your crankshaft down here, and all the force is being transmitted along your connecting rod. So this thing is actually pushing into the side of your cylinder. It's not pushing around the entire thing. It's going to push on one side in particular, and you can actually see how this piston is worn down, and clockwise versus counterclockwise. So you'll have a major and a minor axis of which side it's really rubbing against. So you can actually put a little bit of a bulge on the side that it's pushing against that cylinder side. Before adding on the skirt, I'm going to go ahead and make all of these axis planes visible. And we'll go ahead and I'll choose the x-axis to be the thrust axis, or the long side of our ellipse. And 90 degrees to that will then be where our wrist pin will go. So opening up the ellipse, we're going to click on the center, then on the long side of the ellipse, and then on the shorter side of the ellipse. And if we are really going to get technical on this, we would look at the expansion and forces, but I'm going to just put this in here as a point that it's an ellipse for the skirt of this thing. Extruding this down, if you get into the advanced properties, you can actually put a taper angle on this extrude. Now this is going to be very slight for the piston, like 1 degree. Here's 10 degrees, so you can see which way it's slanting. So the bottom is larger than the top because the bottom is colder and is not going to expand as much in the engine. I'm going to extrude this down 21/16 of an inch. The entire piston was 2 inches high. So if I subtract off that 11/16 from 2, this is where the height of this thing is going to end up. The wrist pin is going to be traveling along the shorter side of the ellipse. So what I will do is go ahead and create a new working plane that is offset from our centered plane. So if you remember what the diameter of this was, it was 3.5, which means that the radius was 1.75. I'm going to go ahead and bump that new plane off to the side, 1.75, and then I'll go ahead and draw in where that wrist pin is. So starting up a new sketch, and I'm going to go ahead and bring this down with a construction line from the base, and the center of that hole is 7/16 of an inch from the base of that cap. Going to a circle, turning off construction line. The radius of the wrist pin is 7/8 of an inch. Finishing out that sketch, I'll go ahead and push it through the entire piston. So I'm going to go ahead and overshoot that to make sure it makes it all the way through to that other side and turning it into a cutout. Okay, and there is our wrist pin hole. Carving out the base of the skirt using the same working plane, I'm going to project geometry to get to the bottom edge to pop up. And the base of this is 2.5 inches, or half of that will be 1.25 inches, and then up 5/16. I'll then go ahead and draw another line for the other side of this just to create this box. So 1.25 inches, making sure everything is centered and straight horizontal. And I'll go ahead and draw the rest of this box. I'm going to use lines, so I'm sure not to draw 2 lines over another. And this will actually let me draw the lengths of these to line up with what's already there. Hitting escape and then turning everything into solid lines. The final thing to cut off these corners, I'm going to use a chamfer edge. The top is 0.25 and the side is 5/16. Distance 1 is the first line you click on. Distance 2 is the second line you click on. So again, chamfer edge, 0.25, 5/16. So click on the first line for the first distance, and then the second line will apply that second distance on there. Finish sketch. Make sure that we have all solid lines in here before we move ahead. And I'm going to extrude this out just like the wrist pin hole. So making it a cut, and there we've gotten rid of some of the weight on the piston, making it a little bit more energy efficient. The next piece, carving out the wrist pin boss. This is going to be a rectangle that's going to push into the side of our ellipse. And we're going to go ahead and start this rectangle 1/16 of an inch underneath that top extrusion. It'll go down 14/16 of an inch, and that will give 1/16 on both the top and the bottom of this. So go ahead and use some construction lines. Make sure those are oriented at exactly 90 degrees, straight up and down. Now remember, the side of our ellipse is not straight up and down. This was a tapered extrude with 1 degree difference from top to bottom. So it's not going to be a good idea to grab this at just the side. I'm going to overlap it. The important part here is the 14/16, the height of the rectangle. And then I'm going to just smush the whole thing into the side of the ellipse. So I've kind of overlapped the edge, made it longer than it needs to be, and I'm pushing it in 1/2 inch here. Okay, looking at this thing when it's done, that bottom lip looks pretty thin and fragile. And if you look at the piston itself, I'm going to go ahead and use a fillet edge. And this is just an artifact of manufacturing process for these. You're not going to get sharp edges down here. You don't need them on the base. So here's a fillet edge, 0.125 inches, just 1/8 of an inch radius for fillet edge. And that will make it a bit stronger around where that wrist pin is going to go. Okay, this was on each side of the piston. So rather than redrawing it, let's go ahead and find that center plane. make that visible, and we can use the mirror command on this. So opening up the mirror command, and you can actually select multiple features right off the left-hand side of your screen here. And I'm going to use that center plane for the mirror plane. Okay, and now we have the same cutout on each side of our piston. For this next piece, we're going to use the shell command. So the piston is not solid, and the thickness of the wall looks like 1/8 of an inch. I'm also going to remove some faces on this. So this will alleviate work in the future. Holding down my shift key and pushing on the scroll button allows me to rotate. You can rotate while in the middle of one of these editing commands. So this is what we're after, is shell 1/8 of an inch thick, and we're going to remove all of those base faces before hitting OK. One more thing, we need to make room for the connecting rod to fit up inside of here and be connected through the wrist pin. So I'm going to go ahead and start a sketch on this base plate. And how far away from the center we're going to be. So it's 7/8 of an inch total, or 7 divided by 16 for half of that. And we need to carve out a rectangle. And again, I'm going to kind of overshoot this because the width of it is what's important. So again, coming over 7 divided by 16, which is half of 7/8. And I'm going to overshoot my rectangle, just making sure that we'll end up with 7/8 at the end of this. I'll go ahead and get rid of those initial lines. Make sure I have just a rectangle to extrude here. And we'll push this up all the way through. Let's see, so it had a height of 2. I'm going to go up a height of 1.75. So that's not punching through the top of this thing. It should be 1/8 thick through the top. And I'll turn this into a cutout. And that is where our connecting rod will come up into the inside of this piston and connect with our wrist pin. The last thing is to walk around and add some fillets to all of those sharp corners on the inside. And this is just going to give the piston some strength. There's a very large force. You're moving a 3,000 to 5,000 pound car around with this little thing, and the entire force comes through this piston. So we want it to be lightweight and energy efficient. So some of these engines are made out of aluminum now. They used to be out of steel. Lightweight makes a big difference, but we don't want it. A lot of times it'll start cracking at any sharp edges. Okay, and that should finish out our piston design. So pretty neat. A couple more things you could add into here is some little holes where the oil can make it through. So you have the oil control ring is this third ring down here, and there would be a hole drilled through the side for the oil to come through. Make sure there's a little bit of room for the oil to come into this wrist pin. So a couple little oil holes, but other than that, we're done.